Okay, in this video, I'm going to talk about the tangent and the length of a curve. Okay, so in the previous video, I talked about how to represent a curve in a parametric form. So, for example, if I give you a curve, this is a curve I give you as example over here. Let's see, this is a curve. Okay, it's in red color. Okay, starting from a point, and there's a curve and ending at a certain point. Okay, so a parametric representation of the curve means that if I can write this every point, if I pick any point on the curve, I sort of draw a vector starting from the origin to that point, and this will represent a vector. If I can draw many vectors along the way for that created the curve. Okay, so any point on the curve, a series point on the curve, I can actually represent every point over here by r sub t, which is, let's say in the 2D space, is xt and y sub t, and by letting t move from t0 to tf. In other words, if the beginning point will be r of t0, which means it just replace the t here by t0, you compute x t0 and y t0, and you try to figure the vector. This will be this vector. So as the t moves continuous from t0 and tf, so you actually kind of figure out, you actually can calculate all the possible points from the beginning until the end. You actually cover every point in the curve. That's what we call parametric representation of a curve. Okay, so apparently this is not unique. You can have many ways you can represent the curve in a parametric form. Okay, so this is for 2D, and you can also extend it to the high dimensional case, n-dimensional curve, which means I have r sub t, which is r1t, r2t, rnt. So this one, they are all scalar function of t, and when you let t move from t0 to tf, it will create a curve, maybe in a high dimensional case, not just in a low dimensional case. Okay. All right. So to give an example, how we use the curve, the parametric form to represent a curve, I can give you an example of that. For example, if I give you r sub t, which is cosine t and the sine sub t, if I let t move from 0 to 2 pi, okay, so basically this represents the circle. The reason that is a circle, because if I talk about this, this will be like xt, sort of, this will be y sub t, okay, this is x sub t. So you do xt squared plus y sub t squared, you give you 1, because sine cosine squared will be equal to 1. In particular, if our starting point, what is starting? Starting point, if you let t to be 0, okay, because that's the starting point over here. So my cosine t will be, cosine 0 will be just 1, and the sine t will be just 0. So your starting point will be 1, 0 basically, so which should be this point. So this is your starting point. So as t goes up, actually each t moves, the cosine t becomes smaller and sine t becomes larger. You're actually going up. You're going up, go all the way circle, and then go back to this point. That's the curve we're talking about. Okay? So that's the curve. The blue curve is the r sub t given by cosine t and sine t with t between 0 and 2 pi represents. Okay. Now let's talk about what is the tangent. Okay, the tangent vector. Let's first talk about the tangent vector, then I'll talk about the physical meaning. Okay, the tangent vector at a point on a curve r sub t is given by just a derivative of the vector with respect to t at that point. Of course, you have to evaluate at that point. So I want to emphasize here is you want some t is some value. Okay, t is equal to some value. Because you evaluate t to some value. Okay, you can evaluate at that point. Of course, this is t some value equal to some value. Okay. Okay. So how about the physical meaning? The physical meaning of the tangent vector. So if I give you, let's say this is the curve I give you, the tangent vector v sub t, the computational y is given by this. We already talked about how to compute it mathematically. The physical meaning of that is a line that only touches the curve at point P, and the direction is determined by the trend of the curve as t increases. Okay, so that means that two things we want to talk about. First of all is the only point. So let's say since the tangent vector defined at a point, so let's say I have this point, so I want to compute the tangent vector on the point, on this point. So first of all, there are two things, because this is still a vector, so there are two things. First one is direction, right? So first of all, it actually starts with the points, and it only touches a point, touches the curve at this point, which means you actually have only two possible ways you can do that. One is you could do the one I showed in the red color. The other one you can also do the opposite. Let's use this color. You can also do opposite. Let's use this color. So you can go this direction, because if for any other direction, you may touch the curve in multiple ways. Okay. For example, if I do this, if I'm doing move this one a little bit, like this. Okay, so essentially you might touch this one at a future point. Okay. So similarly, if you do, I'm going to do this direction. I'm going to move this direction. So you may end up this line will actually touch this curve at a certain direction. Only you only touch this one at this point, then it means that's a direction. Okay, and also because there are two directions, you could also touch as a point only along this direction or this direction. Which direction should I use? The direction is determined by the trend of the curve as t increases. For example, if this is my t0, this is my tf. So as you can see, as t moves from t0 to tf, you keep growing. So which means if t grows, I should move along this direction to the right, not to the left. So which means, hey, my direction should be like this. Okay. So the tangent vector actually talks about tells the direction. Sort of you can interpret it as this. It's like if my object, there's a particle object somehow moving along this curve, and if you let it, what it's trying, for example, the tangent vector is the vector that determines what is the object, where the object is moving to. If you let it go, let's say you're following the trend you already have. For example, you move from here all the way here. Then you don't, afterwards you don't decide to go to this curve, follow the curve. You keep the original momentum to see where it's going. You sort of see you can also interpret this as the current momentum. Current momentum for the object moving along the path. That's what it means. Okay. Alright, so let's then talk about how do I compute the tangent vector. Of course, after figure the physical meaning, after the physical meaning is a little bit difficult to understand, but the actual computation is really straightforward. You just take a derivative and then you evaluate it at a particular point. Okay. For example, if I want to compute if I give you a curve which is given by 2D, which is t and t squared. Okay. So I want to compute a tangent vector at points when t is equal to 1 and t equal to 2. Okay. So first of all, if I calculate that, so I want to have this t is equal to 0. So first of all, the point I'm referring to when t is equal to 1, t equal to 2, they are when r sub t equal to 1 and 1, because you just replace t by 1. Okay. And when you take a derivative of v sub t, of the r sub t, that gives us the tangent vector. Of course, you evaluate at the particular point, which is t equal to 1. So my v sub t when t is equal to 1, which is the tangent vector, is the same as the derivative of the r sub t with respect to t when we evaluate this derivative at t equal to 1. Okay. So when I have that one, because the derivative of that one, derivative of t with respect to t is 1. Okay. Derivative of t squared with respect to t is 2 sub t, 2t. Sorry. Then I have to evaluate at the value when t equal to 1. Which should give us 1 or 2, because the first one is constant, the second one, if you replace t by 1, I get 2 over here. In a similar way, when t is equal to 2, I can compute the point, okay, where it is located at. This is where it's located. And the tangent vector for these points can be calculated as the derivative of r sub t with respect to t when we evaluate the derivative at t being 2. Okay, so again, the derivative is still 1, 2t, and the difference is t now has become positive 2. So I have 1 and 4. That's my tangent vector. Okay, so they're different. Okay. Next, let's talk about what is a tangent line. So tangent line is a little bit your tangent vector is just this vector. Okay, just vector, because vector you can move it at any point, right? It just means this vector. Well, tangent line is just specific this line. Okay, you have to specify this line. So tangent line is quite straightforward actually. Its tangent line is of a curve at a point P. It's just whatever this point we have. We first have to calculate this point. And also we want to compute the tangent line of the point time t. Okay, let's say this is a line. Okay, because line talk about you can sort of say this is a curve. You talk about what line, because the straight line is a special type of curve, right? Curve. This is a line, right? This is a special curve. Okay. So tangent line of a curve at the point P is P plus the tangent vector times t. That's it. For example, if I r sub t the curve is given by t and t squared, I want to compute the tangent line at a point when t equal to 1. Okay. So first of all, I have to calculate what is this point, because I need to know the vector for this. This is a vector for this point. Okay. This is a vector for this point P. Okay. For point P. Okay. So what I do is just substitute. I just substitute this t by the actual value we have, which means t equal to 1. So this is 1 1, because 1 is 1 squared is 1. So 1 1. This is my point P, the vector for the point P. And my tangent line is just the point plus the tangent vector of the point time. This is time vector t. Okay. So since I already calculated this over here, this is 1 and 2, right? 1 and 2 over here. So I just replace this value, right, by 1 1, and this is just 1 1 2, and time is t. Okay. Okay. So that's my tangent line. So it's pretty straightforward. If I already know the tangent vector, and I know what the point is, it is in terms of vector form. Okay. Let's now move to the length of the curve. Okay. So the length of curve, as you could imagine, is a little bit complicated. For example, if I have the length of the curve, you actually, because it's not straight line, so you actually have to compute a small segment, and you calculate, you do the sum of all the small segments, and then you get the length of the curve. So typically it's pretty straightforward. It's difficult to compute. Okay, so mathematically, I want to talk about it. So the length of curve is represented in a parametric form. Okay, I mentioned r sub t is, you can have two-dimensional, high-dimensional one. It's the xt and the y sub t. So the length of this curve is just given by this. Is integration of t0 tf, the derivative of the vector, and then you take a norm, which means you consider the length of that, and you integrate it over dt. Essentially what that means is I'm trying to use my little tangent one to actually approximate my curved one over here, because my original curve, that's not straight. But if I make it infinitely small, so I can use the tangent line actually to actually approximate the actual curved line. Okay, that's what it basically means. So now I'm talking a little bit more detail about why that's the case. Okay, since I already give this is how you compute it, right? Now I'm talking about why. So why that's the case? I'm going to talk about why over here. So the reason I'm doing that, let's say I give you a curve which is the blue curve. So starting from t, some r sub t, and then I started with when t is t0 and any of the t is tf. So that will define my curve. Okay. So the length of the curve, as you can see, if I represent this small curve right over here, that's this way from A to B. So my curve, the length of the curve, okay, of curve should be represented by this small curve. If I can make it a very small, tiny one, so I can divide it into small curve from A to B. This is the curve A to B, I use a curve. This is a curve, okay? Plus B to C curve, plus C to D curve. I can just actually so on and so forth, right? This is also still, each one is still a curve, length of a curve. But if this is the distance between A and B is really small, the curve and the straight lines are actually really similar. So actually I can write this one sort of as the length of this this curve can be sort of written as AB, this straight line, okay? BC, CD, so on and so forth. So I actually replace this AB curve by a straight line. Okay, the reason I can do that because if I make this and B very close to each other, this is almost the same, okay? So when you do that is, so because I don't know how to compute a curve of this smaller one, it's really complicated, but I can compute a straight line. The straight line from A to B is sort of your current, let's say, again, for this point over here, for the B point, let's say is R vector T0 plus delta T. That's my B point. Vector of B point over here. Of course, this guy will be just a vector of A point. So B minus A will be just the, if you remember the vector relationship plus or minus. So this vector A, B minus A, vector of B point minus vector of A point is just a vector from A to B. Okay? So this is, so this I'm going to just point out right over here. So this R of T plus T0 plus delta T minus R of T0, that's the vector from A to B. Okay, so I wanna, if I want to calculate that, I just calculate the length. Take the norm, that'll be the length, straight line the length, right? And you can keep on doing all the stuff. Okay, so we can do a small change to it is, oh, I can divide by delta T and also multiply delta T. That's okay because that will cancel out, right? So divide this guy will be just a derivative, okay? As you said, the derive this guy with a derivative, but also you don't forget that's a norm, okay? And you time delta T, of course, that's delta T. So when you make the delta T, you let the delta to be really close to zero, approach zero, so you become dt, integration part, that one. That's why the length of the T is just the integration of R dot T norm of dt from when T moves from T0 to Tf. Okay? So that's why that's the case, okay? Let me give you a very simple example to see if that makes sense, okay? Let's say if I give you R sub T, which is cosine T sine T, so this is the same example I give you right over here at the very beginning, which represent a circle basically, right? So as T moves from 0 to 2 pi, so I want to compute the length of the circle of this curve. As you know, it's already 2 pi because this is a circle, right? And the radius is 1, so the length will be 2 pi times the radius, so it's 2 pi times 1. It's 2 pi. We already know it. Let's see, we use what do we derive over here to see if that makes sense, okay? What we do here is integrate from 0 to pi and do a derivative R sub T and take a norm of that and integrate that over dt over T from 0 to 2 pi. Okay, so it's the same as 0 to 2 pi, and I'm going to do the derivative. So R sub T is cosine T sine T, right? You take a derivative, which is the derivative first entry in your vector, which is cosine T d cosine T over dt, which is negative sine T, and d sine T over dt will be cosine T. So this is my vector. I compute the norm of that. The norm will be a square root of the squared of each term. Okay, so it's negative sine T squared plus cosine T squared. Okay, so which gives us sine T and sine T squared and cosine T squared. Okay, so sine T and cosine squared, the sum will be 1, right? So take a derivative, still 1, right? Take a square root, sorry, take a square root, still gives you 1. So I have integration from 0 to 2 pi and 1 and over dt. Okay, because this is the same value, right? This is the 1. So integration of t of 1, you give a t, and you value 2 pi and 0. So this guy will give us 2 pi. So which is exactly the same as I computed. I use our concept, the length of the circle, which means the circle is 2 pi, which actually pretty match. They're actually equal. Which actually shows that the way we compute it this way, that's correct. It makes sense. Okay, so that's the way how we computed the the length of the curve by using this approach. Okay.